All right, in this video, we're going to talk about division of polynomials, in particular long division. So long dividing one polynomial into another, where the polynomial you're dividing into the other polynomial may or may not divide evenly. Okay, so it may be a factor, or it might not. You might get a remainder. And this is super important because when you're factoring polynomials, so factoring a polynomial means you're looking for factors that leave remainder 0. And so it's very important to be able to divide to see if you get remainder 0, not to see if you have a factor. And even if you don't get a remainder of 0, you can still get information about the other possible factors from the quotient and remainder that you do get. So being able to do this is really important. We're also going to go over a shortcut or shorthand method for a very particular kind of long division called synthetic division, which really saves a lot of time. And it's going to be super, super helpful when you have to do this particular kind of division. And it's really important that you learn it because you can save yourself a ton of time in problems for this class and calculus and on. So, and this is going to kind of form the foundation for all the different factorization and results about polynomials that we're going to go over in the next two sections as well. So we're going to start off with something called the Euclidean division. It's sometimes called division algorithm. And I'm going to state it for integers, which should be a case that you're more familiar with, so that when I state it for polynomials, it won't sound maybe quite as exotic. So let me go over what that statement actually says. Euclidean division. Now, this is the kind of modern terminology that's used, Euclidean division. But you may also hear the term division algorithm for this result. Although the name division algorithm tends to be reserved for not just the result that says, yes, there do exist these numbers, but also a very particular algorithm, so a process that computational process you can go through to actually find them. So just the general existence result, just call it Euclidean division. And I'm going to state it first for integers. So what does it say for integers? There's slightly different formulations. So this is not the most powerful statement, but it's definitely it's an equivalent statement that's very commonly used. So it says given integers n and d, and it's very important here, d is not 0, because you can't divide by 0. We're going to divide d into n. So given any integers n and d where d is not 0, and actually, let me even specify it even further so that d is positive. You can divide a negative number into it, but I want to even restrict to a simpler case. Just for some simplicity's sake, let's assume that we're dividing a positive number into something. So it then says that there exists integers Q and R such that something is going to hold. So what is going to happen here? So you might be able to tell kind of what's going to happen by the variable names. These are not arbitrary. N you can think of as that's the number you're dividing into, the number. Also think of it as like a numerator. If you think of the division as a quotient, this is the numerator. D is the denominator. It's also the divisor, the number that's dividing into the number. And Q and R are for quotient and remainder. So this says when you divide one number D into another number N, you get a quotient Q and a remainder R. But they have to satisfy certain conditions. So such that, first of all, the number is equal to D times Q, so that's saying it's a quotient, plus R, and also that R is between 0 and the divisor D, but not equal to it. And actually, these numbers are not just going to exist, they're actually going to be unique. So there's a unique quotient remainder. Let me take a second and just put that in here. I forgot to write unique up here. Let me put unique. Okay, example. Okay, let's say 37 and 5. So if I take n is equal to 37, d is equal to 5, all this is saying is if I divide 5 into 37, I get a quotient of 7 and a remainder of 2. So 37 is equal to 5 times 7 plus 2. N is equal to d times q plus r. Okay, so again, n equals number, d equals divisor, q equals quotient, r equals remainder. Now, sometimes there's an equivalent way that you could state this. If you kind of divide this entire equation through by the divisor, then you have it in kind of a fractional form. So equivalently, the equation could read n divided by d is equal to q plus r divided by d. So in that case, instead of saying 37 is 5 times 7 with 2 left over, plus 2, this would say 37 over 5, the fraction 37/5, is equal to 7 and 2/5. In other words, the Euclidean algorithm is just a way of converting an improper fraction to a mixed number, saying every improper fraction you can convert into a unique mixed number. So not really saying something that's that startling. But the reason I'm going over this with integers is because now we're going to take it into polynomials, and you'll see that it's almost the identical statement. You just replace an integer with polynomials. The thing that's the trickiest is, what do we mean by the remainder being smaller than the divisor? So we have to specify exactly what that means. So for polynomials, it's going to say given polynomials why don't I call them p of x and d of x, where d of x, now you might think, okay, we need d of x to not be 0. Just a second. Sorry about that. So we had the result that, or the stipulation up here that d had to be positive. Here we're going to make the case that d is not 0. So it's not the 0 polynomial. So given polynomials p and d, then there exist unique polynomials. So again, they are unique. Move this. Unique polynomials q of x and r of x, such that, and now this is going to read pretty much identically to what it said above, right? It said n equals dq plus r. So in this case, p of x is equal to d of x times q of x plus r of x. But now here comes the interesting part. This is the condition. This is what makes it a little different. The condition here was r was a non-negative number less than d. So it was between 0 and d, possibly 0. So it's like if you divide by 5, what is this saying? If you divide by 5, you can have remainders 0, 1, 2, 3, or 4. You can't have remainder 5, because that would be another multiple of 5 you could factor out, or you could divide out. So 0, 1, 2, 3, 4. Well, what are the remainders here? Well, here are the polynomials. So what does it mean to be smaller than the divisor? What it means is with either the remainder being 0, so that would be if it divides exactly into it, or the degree of the remainder. So the remainder could be a polynomial. The degree of the remainder strictly less than the degree of the divisor, so the degree of d. So instead of having r less than d up here, you have degree of r less than degree of d. So for instance, if you're dividing a quadratic into another polynomial, your remainder could be a number, or it could be a linear polynomial. It could be 3x plus 5. That's what's new. The remainder doesn't have to be just a number. It could be a polynomial as long as it has smaller degree than what you start with. Now, this still doesn't tell us how to do the division, but it's very similar to long division. So I went over, dividing the grade school arithmetic. 5 goes into 37. Look at the steps that you're doing. You're trying to find like a digit. So you're trying to find, okay, this goes into this 7 times. That's the most that it can go in. 35, and then you subtract, right? So you multiply, subtract, you get a little remainder, and then you repeat the process. So you would bring down the next digit, find how many times it goes in, multiply, subtract, multiply, subtract. So you can do this. I mean, you know how to long divide, okay? So it's the same thing with polynomials. So let's go over an example. So let's divide x plus 3 into 2x cubed. I have to make this much longer. 2x cubed plus 4x squared minus 2x minus 1. Okay, so again, this should be reviewed, but I'm going to go through the steps. You look at the leading terms. So I want to ask, how many times does x go into 2x cubed? So really it's saying divide 2x cubed by x. What do I have to multiply x by to get 2x cubed? Well, that's going to be 2x squared. So 2x squared. Then I multiply. Remember, you have to distribute. So that gives me 2x cubed plus 6x squared. Then you have to subtract. And the way that I do this is I think of changing the signs. So instead of thinking of subtracting and distributing, just think of changing the signs, which means if it has a minus, just cross it to make it plus. If it has plus, what I do is I circle it and put a minus. So minus, minus, and then we're going to subtract. These go away. Those should always go away because that's how you chose it. And now these two are going to give us negative 2x squared. Now we bring down the minus 2x, just like you do in ordinary long division. How many times does x go into minus 2x squared? Minus 2x times minus 2x squared minus 6x plus goes away, 4x. So change, instead of thinking of it as subtracting, the way I always think of it is change the signs and then add, because it's easier to add than subtract. So if you change the signs first, just do that first, and then you're going to add. You're less likely to make a mistake if you break it down into the 2 steps. 4x minus 1. Now, are we done? No, because they're the same degree. I have to keep going till I get smaller degree. Well, smaller degree than linear has got to be a constant. So I keep going. X goes into 4x 4 times, so plus 4. 4x plus 12. And then minus, so I get minus 13. So that tells me x plus 3, or sorry, 2x cubed plus 4x squared minus 2x minus 1 is equal to x plus 3 times 2x squared minus 2x plus 4, all subtract 13. But you could write this equivalently as 2x cubed plus 4x squared minus 2x minus 1 divided by x plus 3 is equal to 2x squared minus 2x plus 4 minus 13 over x plus 3. See the difference between the two. So they're basically saying the same things, just different forms. Often the second form is useful. In calculus, when you have one polynomial over another, you want a long divide, you usually would want it in the second form, where you actually have the fraction, you're writing the fraction as the quotient and then a remainder over something. Okay, so now, in this very particular case, notice we're dividing by x plus minus a number. So if you are dividing by x minus a, which in this case, remember, it's going to be x minus a negative 3, because it's always the opposite. So x plus 3 is equal to x subtract a negative 3. So really what we're doing, we're testing here to see if negative 3 is a root of that cubic. Now, it turns out it's not. Okay, that's fine. But here's an easier way to do this using what's called synthetic division. So synthetic division, I'm not going to go through why exactly this works, but it's based on the idea that the only real stuff going on here has to do with the coefficients, right? Everything else is placeholders. So here's what I can do. X plus 3 is x minus a negative 3. So I'm going to put negative 3 out on, I call it on timeout. Okay, so it's sitting over here. It goes on timeout in the corner. Badly behaved A. And then I'm going to write the coefficients of the polynomial I'm dividing into, the dividend. So 2, 4, negative 2, negative 1. Okay, and then I write this bar. And what I'm going to do is fill in 2 more rows of numbers. Here's the pattern. I first just drop down the 2. Then I do the same 2 steps. I multiply, add, multiply, add. So I'm going to multiply negative 3 times 2 gives me negative 6. And then I add down. 4 and negative 6 is negative 2. See the pattern? Negative 3 times negative 2 is positive 6. Add is 4. Negative 3 times 4 is negative 12. Add negative 13. Now, what do you have at the end of all of this? You've got this, and you've got this. Notice, everything except the last number now, these are the coefficients of our quotient. And you know that you can get this by dropping the degree by 1. So if this was x cubed, this was the x cubed coefficient, you know this one's going to start with x squared. So it's 2x squared minus 2x plus 4. And then look, the very last number, that's the remainder. So minus 13 over x plus 3. Super nice, isn't it? So it's much faster, and it takes a lot less space on the page than going through all that stuff. Now, the only thing to say about this now is this only works if it's specifically the form x plus minus a number, 1x plus minus a number. If it's 9x plus something, or it's 2/3 x, you can still do synthetic division. You have to adjust it. I'll show you one of those. And if it's a quadratic or cubic, if you're dividing a quadratic into something, then you can't use synthetic division. It's only for linear polynomials. Okay, so let me show you now. There's one where you can use synthetic division, but you have to tweak it a little bit. Okay. So let's look at, I just better go to the next page. Let's divide 7x minus 10 into 14x cubed plus x squared minus 30x plus 13. Okay. Now I could do this by long division. I'm going to do it by synthetic division. But notice, it's 7x. So what do I do here? So what you have to do is notice this. If I write this fraction, so all divided by 7x minus 10, I could factor out the 7 on the bottom. So I could get 14x cubed plus x squared minus 30x plus 13, all divided by 7 times an x minus 10 sevenths. And then I can just kind of ignore the 7th. It's like a factor of 1/7. And now I'm just going to look at this stuff. I'm going to say, okay, what is that polynomial then divided by x minus 10 sevenths? Now, you have to use fractions. So you're not going to get away from fractions here. But I can use synthetic division. And then what I can do is I can just put the 1/7 at the end. So remember, so this is really saying it's 1/7 times all this stuff. Okay, so let's do synthetic division now with the 10 sevenths. 10 sevenths is on timeout. And we've got 14, 1, negative 30, 13. Okay, I drop down to 14, and away I go. 10 sevenths times 14. Luckily, 7 goes into 14 evenly. 2 times, so 2 times 10, 20. I add to 21. 7 goes into 21 evenly. I'm lucking out here, so I don't have to deal with fractions. 7 goes into 21 3 times 10 is 30. Now I really luck out because I get 0. 0 times anything is 0, and I get 13. So what do I have here? Remember, these 3 give you the quotient. So it's going to be 14x squared plus 21x plus 13 over x minus 10 sevenths. Now, wait a second. Remember that this was without the factor of a 7th. So what I have to do is then take all of this and multiply it by 1/7. Now, what that ends up doing is on the quotient terms, you end up dividing each of them by 7. Now, 14 and 21 are divisible by 7, so that's nice because it makes integers. But for this one, it's going to end up, you end up distributing the 7 across because it's already in the denominator. So anyway, let me show you. So if you distribute across all this, so these 2, this cancels to make 2, cancels to make 3, and then the 7 here gets distributed across, and so all this is 7x minus 10. It's the original 7x minus 10 that we started with. That's what should happen. So altogether, what can we say? We can say that it is, when we divide this into this, we get a quotient of 2x squared plus 3x and a remainder of 13. So we could say that 14x cubed plus x squared plus minus 30x plus 13, all divided by 7x plus 10, is equal to 2x squared plus 3x plus 13 over 7x minus 10. Okay? All right. So that's how you can use synthetic division, even if it's not x plus minus a number, even if it has an x coefficient. But you cannot use synthetic division if it is a quadratic or higher degree. So let's look at one of those. What do we do in this case? You just have to be more careful. Okay, so let's look at 20x to the 4th plus 16x cubed plus 9x squared, and we want to divide this by 4x squared plus 1. Okay. So let's set this up. So we're going to go 4x squared plus 1 goes into this. Now there's two things to be aware of. You could be missing terms in the dividend or the divisor. It's more important if you're missing them in the dividend that you're really careful. You have to be careful for both of them. But if you have missing terms in the dividend, you really should put the 0 terms. Now notice I didn't put 0x here because when I multiply, when I go and multiply out, I don't really need the 0 there. But I do need the zeros here because I really need to know that I'm putting them in the right spot. It's kind of like if you're dividing into 3,000,007, it's really important that you have the 3,000,007, right? You need those zeros there when you're long dividing to really make sure. So I'm going to go 20x to the 4th plus 16x cubed plus 9x squared. And okay, since the zeros are on the end here, I'm just going to leave it like this for now. Okay, let's go ahead. How many times does 4x squared go into 20x to the 4th? It goes in 5x squared times 20x to the 4th. Now here's the thing. When I distribute across the 1, I get 5x squared. So I do not want to put that in the x cubed. Do not do that. It has to go into the x squared. You always have to have your like terms matching up when you're subtracting or when you're changing signs and adding. So I need to put 5x squared here. And then subtract, minus, minus. Now here's the other thing. Now, when I go to see what's the next one, these two do go away, but don't forget this one comes down. The one that's in between, you still have to account for. Right? So you still need it's like if you're dividing 401 into something, right? You'd still have to account for the digits left. So this will be 16x cubed plus 4x squared. 4x squared goes into 16x cubed 4x times, so plus 4x, 16x cubed plus 4x. Okay, again, be careful. Notice I didn't put it under the 4x squared. I'm going to subtract minus, minus. Actually, let me go minus, minus. These go away. These do not cancel out because they're not like terms. I'm left with 4x squared minus 4x. 4x squared goes into 4x squared once. Plus 1. 4x squared plus 1. Subtract. Minus, minus. And so I have a remainder of, whoops, there we go. I have a remainder of minus 4x minus 1. I know that I'm done. Notice this is not a number, so this was degree 2. I'm dividing a quadratic into something. That means my remainder could be a number, so just a constant, or it could be a degree 1. It could be a linear polynomial. So there's no more to do. I can't divide 4x squared into minus 4x. It goes in 1 over x times. We don't. Yeah. So that means we get that this this fraction up here is equal to 5x squared plus 4x plus 1 plus, now you could say minus and you could factor out the minus and stuff, but I'm going to say plus, and then I'm going to put the negative 4x minus 1 all on top here. The other way to do it is you could say subtract a 4x plus 1 on top because the minus would distribute. I'm just going to say plus a minus 4x minus 1 over 4x squared plus 1. That makes it clear that the minus signs are part of the remainder there. All right, I think I'm going to do one more, and I want you to pause the video and try it on your own. Okay, so I'm going to write another one with a higher degree. It's going to be another quadratic dividing into something, and I want you to try it on your own, and then we'll go over it. So let me give you this. All right, so I would like you to divide x squared minus x plus 7 into x cubed plus 6x plus 2. Okay. and see what you get from there. So go ahead and pause the video, try it, and then come back. Okay, hopefully you were able to do this. Let's go over it. So we're going to divide x squared minus x plus 7 into x cubed. Now, because there's a missing term in the dividend, I really need to include that 0. So plus 0x squared plus 6x plus 2. How many times does x squared go into x cubed? X times. I distribute across the divisor. So I get x cubed minus x squared plus 7x. Then I subtract, minus, plus, minus, change the signs and add. X squared minus x. X squared goes into x squared once, plus 1, giving me x squared minus x plus 7. Change the signs and add. Both of those go away. Now, the second one didn't have to go. It just happened to here. And I'm left with a minus 5 when I add. So the 2 and minus 7 make negative 5. So this tells me that I get that this is equal to, you should have gotten, this is equal to x plus 1 minus 5 over x squared minus x plus 7. So the remainder here was just a number. It could have been a linear polynomial like it was before, but it turned out not to be. All right, now what we've done here, besides the statement, the precise statement of the Euclidean division, this should have been what you've gone over in algebra. So this, if you really remembered it well, you understood it, and you remember it, there might not be anything new here. But now we're going to go over two things that maybe are new. These are two results. They're called the remainder theorem and the factor theorem. And these are important results about polynomials. So let's start talking about those. Okay, so the remainder theorem has a deceptively simple kind of statement. It says, given polynomial p of x, and just any number c, let's say, and c, just say a real number, then it says that p of c, in other words, the evaluation of the polynomial at c, if you substitute c into the polynomial and evaluate it, is equal to the remainder obtained when you divide p, the remainder obtained by dividing p by the linear polynomial x minus c. Okay, so this is super important because it shows that there's a relationship between the values of a function and the factors of the function. And this is key because what it means is that solving equations, so because every polynomial equation, you can get everything to one side and you're finding zeros. What it means that solving polynomial equations is really an equivalent question to trying to find factors of polynomials, which are slightly different question, but this is saying that they're really equivalent. So this is not very difficult to prove. All you have to do is say, okay, just divide. So we know that p of x is equal to x minus c times q of x plus r of x. This is just the Euclidean division. And now you just substitute c. Substitute. I can spell. Just a second. substitute x equals c. What does this equation become when you substitute x equals c? It becomes p of c is equal to, oh, and by the way, this r of x, we actually know that it has to be a number. Why? Because the divisor is a degree 1 polynomial, and the remainder has to be smaller degree. That means it's degree 0, a constant, or 0. So this is actually just r, a real number. So it says p of c is equal to c minus c times q of c plus r. But of course, c minus c is 0. This is 0. 0 times anything, big fat 0. So p of c is equal to r. That's it. So let's look at an example. Evaluate p of x equal to, let's say, 5x cubed plus 14x squared minus 10x plus 6 at c equals 2. Now, of course, we could evaluate this the long way, right? We could just say p of 2 is equal to 5 times 2 cubed plus 14 times 2 squared minus 10 times 2 plus 6. The point is, look at how many operations involved. They're powers. Powers are repeated multiplication. So if you're programming a computer to do this, never mind by hand, but if you're programming a computer to do this, think how many operations. But what if it's a 21 degree polynomial? So you have to raise a number to the 21st power, and then the 19th power, and the 16th power. We don't want to do that. That's going to waste energy. That's going to be computationally bad. Remember, synthetic division, because we're just going to long divide. Synthetic division is just multiply, subtract, multiply, subtract. There's no repeated multiplication in it. And you only go up to the degree of the polynomial. So there's very less computation involved. So it may not seem like a big difference here, but it really is. 5 times 8. Okay, so this would be 40. Okay, 14 times 4, 56. You can even see here that this is going to take a little bit longer than the other way. Plus 6 is 96, and 6 is 102 minus 20. Okay, so we get 82. Okay, that's fine. Now let's look at it using the remainder theorem. Here's all you do. 2. And then you list 5, 14, negative 10, 6. Okay, this is just a setup. And now just do synthetic division, and we're going to see what is the remainder over here. Okay, that's what we're looking at. That's going to be 82. What's in there? That's going to be 82. Watch. 5 times 2 is 10. 24 times 2 is 48. Subtract 10 is 38. Times 2 is 76. 76 plus 6 is 82. You can see right here, this took me much less time than taking the powers. So it's a very nice result. And it's not just for evaluating polynomials. It leads to another result that's even more important. And that's called the factor theorem. So what does the factor theorem say? So the factor theorem says, look at the remainder theorem. Look at what the remainder theorem says. And notice that in this statement here, what would it mean for x minus c to exactly divide? In other words, for x minus c to be a factor, that would be the case if the remainder was 0. But the remainder theorem says that the remainder will be 0 if the polynomial is equal to 0. So what we're going to see is that the polynomial is going to have a 0 if and only if x minus c is a factor. In other words, there's a relationship between the zeros of a polynomial and these linear factors of the polynomial. Okay, let's state what that says. So it says, given polynomial p of x and let's just say real number c, just c in the real numbers. Then x minus c is a factor of p if and only if, so remember this double arrow means goes both ways. So if you have one, if one's true, the other's true, and vice versa. If and only if p of c is equal to 0. And the proof, I just explained it to you. So just, take the remainder theorem with r equals to 0. I mean, just take the statement of the remainder theorem and say, well, what does this say if r is 0? And that's exactly what the factor theorem says. Okay, so let's look at an example where we can use the factor theorem. Okay, so let's use the factor theorem to show that x minus 5 is a factor of this cubic polynomial, x cubed minus 4x squared plus 4x minus 45. And in fact, then, once we divide that into it, we show that it's a factor, we're going to get a quadratic. Once you get down to quadratics, you're done. Because you can either factor it or use the quadratic formula. Now notice this cubic. This cubic, you might think, well, it's 4 terms. So in algebra, you would try and factor this by grouping. Does that work here? If you group the first two together, you could factor out an x squared, and you'd be left with x minus 4, but that doesn't really work with the last two. If you take the first and the third, you could factor out an x, you have x squared plus 4, but again, that doesn't work with the second and the fourth. And if you take x cubed minus 45, you're really out of luck. So we can't do this by factoring by grouping. So there's no beginning intermediate algebra technique that you usually cover that will allow you to factor this. But we can show that x minus 5 is a factor. Now, how would I know to get x minus 5? Well, that's what we'll go over in the next video when we talk about things like the rational root theorem, Descartes' rule of sign. So we'll get into that. How would I know to pick 5? I'm not guaranteed that 5, I mean, you can guess 5, but you're not guaranteed that 5 is going to be, but you can check. And that's what we're going to do here. So the way we do this is 5 goes in the corner on timeout. 1 minus 4, 4 minus 45. So I use synthetic division. 1 times 5 is 5, adds to 1, times 5 is 5, adds to 9, 45, 0. As soon as I get 0 there, that's what I'm looking for. When you're doing these factoring problems, in the next couple sections, you synthetically divide, you're looking to get 0 in that last one. Now, what does this mean the quotient is? It's x squared plus x plus 9. So that means x cubed minus 4x squared plus 4x minus 45 factors as x minus 5, x squared plus x plus 9. And this quadratic here does not factor over the integers. In fact, it doesn't even factor over the reals, right? Because its discriminant is negative. It's b squared minus 4ac would be 1 minus 36. So it's clearly negative. So it does factor over the complex numbers. So when you're talking about does something factor, you have to be clear. Do you mean, does it factor further over the integers, over the real numbers, over the complex numbers? It makes a difference what field, we would say, you're trying to factor it over. In this case, let's say we're just factoring like in high school algebra over the integers, we'd be done. And even if we were factoring over the real numbers, we'd be done because it's an irreducible quadratic. So we can't do anything more with this. Okay, so these are the fundamentals of factoring in pre-calculus. And of course, the factoring in pre-calculus, then when you get to calculus, you really need to be fluent in all this stuff so that when you need to do these factorings and finding roots and all sorts of these type of things, you can do it without having to stop and remember how to do it. So in the next video, we're going to go over 3 super important results. Well, there's one that's really, really important. The other 2, you can get by if you don't remember them all the time. But the super important one is the rational root theorem, which will give you a list of candidate roots that could be integers or rational numbers. And then there's other 2 that are useful, but you don't use all the time, but can be helpful sometimes. And so that's what we're doing. We're trying to get these results so that we can get a toolkit of ways of trying to find roots of polynomials, which leads to factorization of polynomials. Okay,